Good morning. My name is Lahari. I am working as a software development engineer in testing at PGH from past 2 years. So today I am here with Keerthi, my co-speaker.
Good morning, everyone. My name is Keerthi Sita. I'm working as a software engineer at Open Source DB. In this session, I'm going to talk about multi-master distributed database systems, which includes challenges, core design principles, and best practices, and also important considerations. So before we go to this diagram, I just want to know how many of you are aware of multi-master replication. So I can see the less hands in this room. So I just want to explain what is multi-master replication is. First of all, replication is the process of copying data from one database server to another database server. And in the left side, we can see it is a single master replication. In the single master replication, the master only can write and all other nodes are read-only replicas. The data flows in one way from master to replicas, and it is simple, reliable, and it has strong consistency. Wherein in the right side we can see multi-master replication. In the multi-master replication, all nodes uh, all nodes does reads and writes operations. Data flows in bidirectionally between the nodes, and yeah, it has some challenges. We'll see in the next slide. So multi-master design challenges. First one is conflict resolution. When we update the two nodes at the same time, when we update the same data at the same time, then we get conflicts. If if you don't have any rule to decide whose change wins, it is a risk to override the valid data. So you need some strategies to overcome this, and we'll talk about the strategies later in the next slides. About data consistency, in global multi-master systems, you usually get eventual consistency. Like all nodes matches eventually, but not instantly. The strong consistency is possible, but it often sacrifices the performance or availability. The replication latency in the global multi-master setups, like it takes time to travel the update takes time to travel between the nodes, and if all nodes doesn't matches, it can get conflicts. When we come to performance, the replication is not free. Every time the data is written, it has to be transmitted, captured and transmitted, and it has to applied in the replicas. So it consumes CPU memory and CPU memory and network bandwidth. So it consumes these things. When the nodes grows, uh, or like when we say the network, like it takes synchronization cost, like to, for performance. And when it comes to topology complexity, like multi-master is not like multi-master is not like connect everything to everything. It often, sorry, it has some options like you need to know how nodes get communicated. It has some options like mesh topologies and hub and spoke and hybrid topologies. So there are some core design principles for the multi-master systems. There are consensus mechanisms. Consensus is agreeing all the nodes on a change. The two-phase commit is either accepts all the commits or it's rollback. In the raft and boxes, it it is like it uses a leader and it uses a leader on every agreement. If one node gets failed, it works as usually. The system get never slowed. But in the two-phase commit, it gets slows if it gets stuck if one node is get failed. Before we discussed about conflict resolution strategies, like conflict resolution, now we'll discuss about conflict resolution strategies. There are some strategies like last right wins, which keeps the latest update, and application specific rules, which is like high score wins, and quorum based commit. In this, the major nodes has to get agreed to the commit and uh, replication models. The synchronous needs acknowledgement from the target node. It is lower, but it has strong consistency. In the asynchronous, it doesn't need any acknowledgement. It is faster, but there is a chance of losing data. In the hybrid, it is a mix of both, and it like some nodes can sync instantly, others will catch up later. In the partition tolerance and availability, there are uh, algorithms like Packers and cap theorem. Cap theorem is like in the network partitioning, we must choose only one between availability and consistency. In the Packers theorem, in the network partitioning, we must choose consistency and or performance or either availability. As it is sharding and load balancing and automatic failover. These are the best practices of multi-master systems. I'm going to discuss about understanding the trade-offs of consistency versus availability. We need to understand the trade-offs of this both. Like in the perfect world, you want your system to be always consistent and always available. But in the distributed systems, you have to only choose once, as I said before. Like if the network partition occurs, if you are in the if the network partition occurs, you must choose accepting rights. You either choose accepting rights, which which maintains availability, or you must stop accepting rights, which maintains the consistency. Like and choosing the right replication model based on the use case also is a best practice. Like every app doesn't need multi-master. If your app is simple, lives in one region, single master is enough for your app. But if your app is multi-users, have multi-users and lives in multiple regions, the multi-master is what you need. Optimizing for performance and conflict resolution. you just you just made your replication setup. It's not that the replication is safe. You need to think of what are the optimizations you need to have. Like, you don't let all the nodes to update, like two nodes to update at the same time, same data, which causes the conflicts. And split the data by users or regions if possible. These are the things. And regularly monitoring and is what the best practice is. Monitoring makes, like, before the problem occurs, you need to monitor the system. You need to think of, like, what if one node crashes, what if one connection drops. These are some important considerations before choosing the multi-master system. Like, application compatible with asynchronous logical replication. Like, PGH uses POC. You need to think of, is your logical replication is like PGH uses POC with asynchronous replication. It ensures you should need to ensure all replicated tables have primary keys, which identifies the updates and uh, updates. Is workload relatively conflict free? Like, is there are only few cases of getting conflicts. And you need to consider, is it open source or proprietary? Like, open source is PGH and proprietary is EDB. Uh, and you need to consider, is the distributed database solution is Postgres based or Postgres compatible. Postgres based is fully Postgres, and compatible is almost Postgres.
Thank you, Kirti. Yeah, thank you, Kirti. So till now, Kirti has given some basics about the replication. Well, so Kirti has given some basics about it was switched to. This is on. I think now I'm okay. Yeah. So yeah, many of you are aware of what is logical replication, what is asynchronous logical replication. So I think so here in multi-master we use asynchronous logical replication under the hood. So let me give you a small or just a bit of what is logical replication. So if you see this image clearly, it says it's nothing but an replication, publisher and subscriber model, which is nothing but an logical replication. So we all know that how this logical replication architecture actually works. First, it just takes the snapshot of the data from the publisher side, and then it copies that data to the subscriber side. And this is done in a real time in order to guarantee the transactional consistency. So this is what PGH is more of using. So before even giving about this logical replication, so PGH has basically two products. One is PGH Cloud and the other one is PGH Platform. So now we are completely focusing on the PGH Platform. So this is what, and yeah. So in PGH Platform, we have got several extensions in it. So the major one here is Spock, and then we come up with Snowflake, LOLOR, ACE, and also these are all built on standard Postgres engine. So what does a Spock extension actually do? So in multi-master replication, the general problem we all face is this conflict resolution. So here we have the last update wins. How do we do that? So generally, for example, we have multi nodes. Suppose the writes are happening simultaneously on all the nodes, and obviously there will be an conflicts, right? So we have an GUC named spock.exception log and spock.exception behavior, where we can set these GUCs to the values like discard, all, none, or trans discard. So based on our requirement, whether it can store all the conflicts to the to the table, so that we can go back and refer to that table, and we can clearly see what type of conflict it is, whether it is insert, whether it is update, or what kind of, or else we can also see the type of conflict, and along with the timestamp. So for time being, I cannot show you the demo here, but I have an other demo which covers this. And also in this POC extension, there are three exceptions that are covered. One is primary key exception, and the other one is auto DDL exception. DDL exception. So this is one thing that can be taken care of by Spock, and the other one is LOLOR, which means large object logical replication, and the other one is ACE. What does this ACE do? So in multi-master, there might be a chance that one node can go down for the reason of replication lag or node failure or whatever may be the reason. So in order to find the differences between the nodes, there is an extension named anti-chaos engine. So with this extension, we can just go through. For suppose we have a table one inserted in N1 and the table in other node, you can just get the differences by just giving that command line tool like ace table diff and give that table name. You can see the differences clearly. So this is one extension. And let me quickly get to the demo. So this is a two node setup here. So this is what you are doing. You are just trying to do the PGH setup with this curl command. And the latest CLI version we have here is 25.2.0, which is going to get into the download in few days. But right now here it is 25.1, and you can see that. And we also, and this can be installed on different OS like Rocky Linux, Ubuntu. Nothing changes. No more changes in any steps. The steps were same, and you can see. And this is compatible for both ARM and AMD architectures as well. This is done on node 1 right now, and the same thing is done on node 2 as well. And if you go for PGH info, you can clearly see that what was installed what version of Python it is supporting, and the CLI version as well. Yeah. So now we are installing the latest version, PG. I think it's PG 18 right now, but it's PG 17 right now. We are doing installation of it, and then we are just trying to do the initialization. And here you can see clearly that when we try to do the PG 17 initialization, it, and also we are doing the installation of Spock. Spock extension is installed here, and you can see I already mentioned that we are using asynchronous logical replication, where we can see the volume logical, which is very basic, and the Spock extension is now gone into the shared preload libraries, and you can also see here Spock.conflict resolution is last update which I earlier mentioned about the conflict resolution. And the same thing, now it's done. So you can see here the all the extensions that are installed through the PGH setup. Snowflake and Spock are the two default versions extensions that are installed, and you can it also supports 20 plus extensions, and you can do it through update manager. You can do it manually. And now I'm creating two nodes here, N1 and N2, and I'm just cross wiring by creating the subscriptions between the two nodes, and one should be very careful by creating the subscriptions. I'm doing this setup on EC2 instances, where we need to be careful while giving the IP addresses from N1 to N2 and N2 to N1. And after cross wiring this, I am just setting up some GUC values, and also here you can see that from Spock dot subscription, we can see that sub here is sub N1, N2, and the details of it. This is on N2. Yeah, this is on N2. And also, I am setting up these some GUC values to enable auto DDL, which means that create table command gets replicated. So all the DDL commands get replicated from N1 to N2. Let us by giving this enable DDL replication and include DDL replication and setting allow DDL replication to on. So I just created a table here, and you can see this DDL statement got replicated, and it got created on the other node as well. So now you can see that we can have two tables on the other node, T1 and T2. And then I'm just doing some insertions on T1. Yeah, so if I do drop table T2 on one node, it just get drops on other node as well. So yeah, so this is a very quick demo for time being. So please, if you get any doubts, you can reach out to us. We'll be around here. Me, Keerthi, and Hari will be around.